Okay, so in the previous video, we talked about forces, and we talked about the nature of force, and we mentioned this whole idea of this, a lot of times this is called Newton's second law, but Newton second. And it says that the total force on an object is equal to the mass times acceleration. Force is a vector, and acceleration is a vector. And in the previous case, what we did was look at special case where F net is equal to 0 vector. Okay, so that would be equilibrium. But now we want to talk about when this is not true. We want to talk about when it's not in equilibrium, and that means that we need to look at acceleration. So this video is really about what is acceleration. So let's start with an example, because we need to talk about three things: position, velocity, and acceleration. Okay, so let's start with position. So if I have an XY axis right here, and I have a ball, and the ball is right there, I can define the position of the ball using the symbol R, the vector R. And we use R because, if this is, it looks like polar coordinates, you don't need to know that, but that's part of the reason why. But we like to use R. We don't want to use X because that would be the X component. We don't want to use Y because it would be the Y component. So in general, I can say the vector R is equal to its X value if it's from the origin. So it'd be X, Y, Z. So that ball, it could be anywhere. But now imagine it starts right there at time 1. And then it goes over here, and now it's right there at position 2. So let's call that R1. R1 is going to be X1, Y1, Z1. They're numbers. Now a little bit later, it's over here at R2, where that's going to be the vector X2, Y2, Z2. And I want to somehow describe how this thing moves. Well, I can define the displacement. The displacement is the vector from 1 to 2. And we're going to use the symbol delta R. And so in physics, delta means change in. It's raining. Delta, that symbol, the Greek symbol delta, means change in. Whenever you see delta, that means change in. And that's a capital delta. Okay, we're going to learn some Greek letters just for fun. So this means change in R. So delta R is going to be, it's always going to be final minus initial. So the final position's R2 minus the initial position R1. Now there's something really important about this. Imagine that I change my color to green. And in green, I have another x-axis. Let's say I put my x and y axis over there, so I have a new origin. That's my new origin. So in that case, R1 is going to be different. It's going to be the green R1. R1 is this. And the second position is going to be green R2, which is over here. However, if I take the delta R in the green axis, in the green coordinate system, it's going to be green R2 minus green R1. But you'll notice that green R1 delta R green is equal to delta R black, which is really nice, right? Because if I want to describe the motion of this thing, in a sense, it shouldn't depend on where my coordinate system is, because that's not even real, right? Coordinate systems are fake, and they're used for us. They're a reference frame for us. And so I should be able to move it to a different location and still get the same displacement, and I do, okay, in this case. There are some cases where you would get a different displacement, but in this course, we're going to use situations where you can move the coordinate system wherever you want. In fact, I could even rotate my coordinate system, and I would still get the same vector displacement. So that's good. It would look a little bit different. Okay, well, who cares about displacement? Well, we all care, because that is how we define average velocity. So let's go back over here and say that I have my ball, X, Y. It goes from position 1, and who cares what path it takes? I don't care about that. So here's my delta R. And so I define average velocity as the change in position, which is the displacement, over the change in time. Now, there's some really important things about this. Delta r is a vector. V is a vector. Delta t is not. But if I, it's not time. It's a change in time, right? Because maybe I have a clock. Here's my little clock right here. And I start this at time of, let's say, t1 is equal to 2.1 seconds. And then a little bit later, t2 is equal to 3.2 seconds. Well, delta t, again, would be the same. Remember, I have delta, that's the change in. So it's going to be t2 minus t1, which is 3.2 minus 2.1, is equal to 1.1 seconds. So my delta t would be 1 second. That's not the time. That's my change in time. That's how long it took to go from position 1 to position 2. And the same thing for delta r. It's the change in position. And that's my average velocity. Now, it's possible that the average velocity could indeed be constant if it moves in a straight line, but it doesn't matter. Okay. So let's get the units on this. If the displacement is a vector in meters and time is in seconds, then this would be in units of meters per second. So the average velocity tells me how the position changes with time. It's the rate of change of position. Now, what if I take a time interval delta t of 0.01 seconds? It's really small. Well, then in that case, if it started right here, it would end up right there. It didn't move very far at all. So as delta t gets really, really, really small, it doesn't really matter if I go straight there or I take some path. They're going to be the same thing. So we actually have, this is another definition. We say v instantaneous is the limit as delta t goes to 0 of delta r over delta t. And this, if you take calculus, this is where you get the derivative from. The derivative is like that. And you may think, well, how can you divide? How can you do this, right? How can you have a vector up here and a scalar down here? Well, you can break this into parts, right? Let's write it out the full way. Let's go, this is, that's t1. Let's say r1 equals, I'm going to use some numbers here, 1, 3, 0 meters. R2 is going to be equal to, let's say, 2.5, 1.50 meters. So in that case, I can find delta r. Delta r is going to be equal to the r2 minus r1. So it's going to be 2.5 minus 1, right? Because when we subtract factors, we subtract their components. Then I'm going to have 1.5 minus 3, and then I'm going to have 0 minus 0. Oops. So this is going to be equal to 2.5 minus 1 is 1.5. This is meters. 1.5 minus 3 is negative 1.5. And then 0 minus 0 is 0 meters. So that's my delta r. Then I can calculate my velocity. I'm going to use this delta t up here. So v average is going to be equal to this 1.5 negative 1.50 meters divided by 1.1 seconds. I should use a better number. So now I can divide each component by 1.1. So 1.5, I don't want to make a mistake. 1.5 divided by 1.1 equals 1.36. So this is going to be equal to 1.36 negative 1.360 meters per second. If I wanted to, I could write it like this. V average x equals 1.36 meters per second. V average y equals negative 1.36 meters per second. I could also write it like this. V average x equals delta x over delta t. V average y is delta y over delta t. Okay, let me tell you what not to do when we're talking about velocity. I'm going to show you some more paper. Okay, if you say this says velocity is distance over time. I just want to point out, I see this a lot, okay? But I'm going to get this. Don't do that. Okay, that's very, very dangerous. There are a lot of cases where this is not true. It may work sometimes, but it's not distance over time, right? So if I did that back on my other example, here at position 1, if I took its position of of 130 and its time of 2.1, and I say 1 divided by 2.1, I'd get around 0.5. That's not its velocity, right? That doesn't even make any sense. The change is super important. This is a rate of change problem. So don't do that. You're going to get yourself into trouble. I promise you, you're going to get into situations that you're not going to be able to get out of. Sometimes it's right. Sometimes it works, right? But that doesn't mean that it's the good thing to do. So don't do that. I don't want to see that. Also that it's not a vector. Okay, so instead, V average is delta R over delta T. Okay, let's go to the definition of acceleration. So just like the velocity tells you how your position changes, the acceleration, A, tells you how your velocity changes. So it's change in velocity over the change in time. So suppose I have a car going this way with a velocity of 100 meters per second, and then a little bit later it's over here and it's going this way with a velocity v1. v2 equals, I'm making up some numbers here, let's say it's 0.5 negative 10 meters per second. So the acceleration is defined as the change in velocity. So it's going to be the final velocity minus initial velocity divided by the change in time. So let's say this is t equals 1 second, and this is t1. t2 equals 2 seconds. So A would be vector v2 minus v1 over delta t, which is v2 minus v1 over t2 minus t1. So let's do it with these numbers. So here we go. So the acceleration is going to be the change in velocity. So v2 is going to be 0.5 minus 1 for the x component, because I have 0.5 minus that component. Then I have negative 1 minus 0, and then I have 0 minus 0. And then on the bottom I have t2 minus t1, so it's going to be 2 seconds minus 1 seconds. So this is going to be 0.5 minus 1 is going to be negative 0.5, negative 1, 0, divided meters, divided by 1 second. So now I get negative 0.5, negative 1, 0. Oh, this is meters per second. Meters per second per second. So it's technically meters per second, but a lot of times we would write this as the acceleration of negative 0.5, negative 1, 0 meters per second squared, because it's like seconds and seconds divided by it. It's really meters per second, but we like to write it as meters per second squared. Okay, so now we know the definition of acceleration. That's the key, right? Because now I can look at a problem like this. Suppose I have some box and I have two forces acting on it. It doesn't really matter what they are, F1, F2. Then I can say F net equals MA. So if I know the net force as a vector, I can solve for the acceleration and say A equals F net over M. Or if I know the acceleration, I could solve for the net force. Maybe I don't know one of the forces, okay? But this is where we're at. This is the last piece for Newton's second law. Now we know the acceleration, and we know what the acceleration is, and we can use it in other problems. Okay, I'm gonna solve some more problems, but really that's the key stuff that you need to know.